Are we alone in the universe? It's a question that has stirred human imagination for centuries, whispered through myths dreamt about in science fiction, and now rigorously explored through science. Since we first looked up at the night sky, those countless shimmering stars have been a mirror reflecting our deepest hopes and fears. Somewhere out there could there be others? Other minds, other civilizations, other lives living beneath alien suns? The universe is vast beyond comprehension. Billions of galaxies, each harboring billions of stars, many with planets orbiting in their habitable zones. Our own little blue dot Earth is the only place we know for certain where life thrives. But the cosmos is ancient, stretching back over 13 billion years, and in that unfathomable stretch of time and space, could life really be unique to us? Or is it only a matter of time before we stumble on proof that we share the universe with other beings? And that is where the real mystery lies. It's not just if life exists elsewhere, it's what happens next. What if one day humanity detects a clear, unmistakable sign, a signal from a distant civilization, or better yet, a direct encounter? How would our world change? How would we respond? Would it be a moment of unity or chaos, hope or fear, opportunity or threat? This video is a journey, a deep dive into the thrilling and sometimes terrifying possibilities of discovering alien life. We'll explore what the science tells us about where and how life might exist beyond Earth. We'll meet the incredible technologies and missions designed to find it, from radio telescopes scanning the skies to interstellar probes searching for signs of habitability. But most importantly, we'll examine the bigger question. If we ever do find aliens, how will humanity react? What will we do? Imagine for a moment the day that changes everything. The day when signals are received, not random noise but a message from another civilization. Imagine the headlines, the excitement, the panic, governments convening emergency meetings, scientists poring over data, trying to decode the signal, religions grappling with the implications, people around the world looking up at the night sky with new eyes, suddenly feeling smaller or maybe more connected than ever before. But it's not just about communication. What if probes or even visitors arrive? What protocols would be in place? How would humanity's leaders respond? Would we extend a hand in peace, or prepare for defense? And what about the cultural impact on art, philosophy, and our own self-understanding? To answer these questions, we need to understand life itself. What is life? What forms could it take in environments far different from Earth's? From microbes in frozen moons to intelligent beings in distant star systems, life could challenge everything we know. The search for it is one of the most exciting frontiers in science today. So buckle up, because this story is about more than just aliens. It's about us, about how we see ourselves, how we imagine our place in the cosmos, and how the discovery of others might transform the very essence of humanity. Are you ready to explore the unknown, to consider the consequences of cosmic company? Then let's begin this incredible journey together. Imagine standing beneath a night sky, stars stretching endlessly. What if, just beyond those twinkling lights, someone, or something, is watching back? How would your world change if tomorrow we found out we're not alone? Chapter 1. Defining life. What does it even mean? Before we can even begin to imagine what alien life might look like or how we might interact with it, we must first grapple with a deceptively simple but profoundly complex question. What is life? It seems obvious. After all, life is all around us. We see it thriving in every corner of Earth, from the tallest redwoods brushing the sky, to the tiniest bacteria thriving in the deepest ocean vents. But when we try to define it precisely, things get complicated fast. Is a virus alive? What about a flame, or a crystal that grows over time? How do we separate the living from the non-living when the boundaries blur? And if we hope to find life on other worlds, we need a definition broad and flexible enough to capture life forms that might be unlike anything we've ever seen. Life that may not even be carbon-based or require water to survive. The scientific search for life. To address this, scientists have developed criteria to identify life, both here on Earth and beyond. These criteria generally focus on a few core features that life exhibits. It must be able to grow, reproduce, consume or utilize energy, respond to its environment, and adapt over generations through evolution. The most fundamental principle is that life is a self-sustaining chemical system capable of Darwinian evolution. This definition, crafted by NASA scientists and astrobiologists, emphasizes life's ability to change and adapt over time, which is essential for survival in changing environments. Yet these criteria do not prescribe what life must look like, only what it must do. Form follows function. This brings us to an important concept known as form follows function. In biology and engineering alike, this means the shape or design of an organism is driven primarily by what it needs to do to survive in its environment. Take flight as an example. The ability to fly evolved multiple times independently on Earth, resulting in a wide variety of wing types. Birds, bats, and insects each developed wings that look very different but serve the same function, moving through air. This is called convergent evolution. Different organisms arriving at similar solutions because they face similar challenges or opportunities. So, if we find alien life, it might not look like us, but it might have analogous features shaped by similar needs. For example, if an alien species needs to move quickly, it might develop some form of limbs or propulsion. If it needs to sense its environment, it might evolve eyes or something functionally similar. At the same time, life beyond Earth might be radically different, so much so that we might not even recognize it at first glance. Life on Earth is carbon-based and water-dependent because carbon atoms form stable, complex molecules, and water is an excellent solvent that facilitates chemical reactions. But could life be based on silicon instead? Silicon shares some chemical properties with carbon and can form long chains, though it is less versatile and stable under Earth-like conditions. Could life exist in liquid methane or ammonia instead of water? Some moons in our solar system, like Titan, have lakes of liquid methane. Scientists speculate that exotic life forms could thrive there, using completely different biochemistry. Some thinkers have even imagined life as patterns of plasma or energy, not matter at all, though this is highly speculative. On-screen text. Chapter title on screen. Scene 17, Dynamic Interactions. Instead of thinking of life as a static object, many scientists now think of it as a process, a dynamic, ongoing set of interactions between molecules and their environment. Life metabolizes energy, grows, reproduces, and evolves. Processes that keep it far from equilibrium with its surroundings. This perspective helps us understand that life might be less about the specific materials it's made of, and more about the processes it performs. Earth's extremophiles: clues to alien life. Looking at Earth's most extreme environments provides clues about what might be possible elsewhere. From the scorching heat of deep-sea hydrothermal vents where life thrives without sunlight, to the freezing deserts of Antarctica where microbes live under glaciers, life shows remarkable adaptability. Some bacteria survive in highly acidic or radioactive environments. Others live miles underground, feeding on chemicals and rocks. If life can adapt to these extremes on Earth, it opens the possibility that life elsewhere might be equally resilient, surviving in conditions that once seemed inhospitable. Viruses, alive or not? A particularly challenging question in defining life is the status of viruses. Viruses cannot reproduce or metabolize on their own. They require a host cell. Outside a host, they are inert particles. Does that make them alive? Most scientists classify viruses as existing at the edge of life, a gray zone between living and non-living. They challenge our definitions but also highlight the diversity of biological systems. Artificial life and synthetic biology. Modern advances in synthetic biology and artificial intelligence raise new questions about life. Scientists have created synthetic cells with minimal genomes capable of reproduction. Others are designing artificial life forms made of DNA, RNA, or other molecules. Could life eventually be created from scratch? If so, how would we classify it? And if we find alien life, how would we distinguish it from artificial life? The role of evolution. One key element that distinguishes life is evolution by natural selection. Life is not just a snapshot of complexity, it is a continuous process of change, adaptation, and survival. Evolution allows life to explore countless possibilities, gradually refining solutions to environmental challenges. This is why life on Earth is so diverse, and why we expect any alien life capable of long-term survival to have undergone evolution. The search for life beyond Earth. With this understanding, scientists are searching for life beyond Earth in many ways, studying exoplanets in the habitable zone where liquid water might exist, analyzing Mars soil samples for microbial life or fossils, exploring icy moons like Europa or Enceladus for subsurface oceans, listening for signals from intelligent civilizations with powerful radio telescopes. Every new discovery expands our understanding of what life might be. So, before we imagine meeting alien beings, we must first redefine life itself. Life is not a rigid blueprint, but a spectrum of processes shaped by environment and function. By broadening our minds beyond Earth-centric definitions, we equip ourselves to recognize life in its many possible forms. The universe is vast and ancient, and if life has emerged elsewhere, it may surprise us in ways we never expected. This is the foundation upon which the search for extraterrestrial life is built, and the question that captivates us all. Think about the strangest creature you can imagine, something completely unlike us. Could it still be alive? If life can wear countless forms, what might alien life look like hiding in the shadows of distant planets? Chapter 2. Life in the Extreme. Clues from Earth's toughest creatures. When we picture life, many of us think of lush forests, warm sunlight, flowing rivers, and the buzzing of insects under a blue sky. These images are comforting, familiar, our everyday world. But to truly grasp the possibilities of life beyond Earth, we have to venture far beyond these gentle scenes, into realms so harsh and unforgiving they were once believed utterly inhospitable to life. For centuries, scientists assumed that life required moderate temperatures, fresh water, a steady supply of nutrients, and an atmosphere rich in oxygen. It was thought that without these delicate balances, living organisms could not survive. But that notion was shattered by discoveries of life forms that seem to thrive where no life should. They live not just in difficult environments, but in extremes that would annihilate most earthly creatures within moments. These remarkable organisms, called extremophiles, redefine what it means to be alive. They invite us to reconsider the limits of biology and offer tantalizing clues about the kinds of alien life that might exist far beyond our planet. Deep beneath the ocean's surface, at hydrothermal vents that spew boiling, mineral-rich water into the freezing abyss, entire ecosystems flourish. Here, sunlight never penetrates, the water pressure is crushing, and temperatures can soar above 400 degrees Celsius. Yet, within these hostile conditions, complex communities of tube worms, shrimp, and unique bacteria thrive. These bacteria don't rely on sunlight for energy. Instead, they harness chemical energy from the vent's minerals in a process known as chemosynthesis. The discovery of such ecosystems revolutionized our understanding of life's resilience and adaptability. If life could survive and evolve in the absence of sunlight, relying solely on chemical energy, then the classic image of life tied to stars and warmth no longer holds exclusively true. It opens the possibility that life on alien worlds could exist beneath thick ice sheets or deep oceans, far from any star's nourishing rays. On the surface of our planet, in geothermal hot springs where water temperatures approach boiling, another group of extremophiles flourish. Thermophiles, as they are called, not only survive but require temperatures of up to 80 degrees Celsius or more to grow. In Yellowstone National Park, these fiery pools harbor bacteria that give rise to vividly colored mats, their pigments protecting them from extreme heat and radiation. The enzymes produced by these thermophiles have even become invaluable to science and industry, used in processes like DNA amplification, which powers modern genetic research. But temperature extremes are only part of the story. Some microbes withstand conditions far more hostile in other ways. Acidophiles thrive in environments with pH values so low they would dissolve human flesh on contact. Acidic lakes and mine drainage waters, with their toxic soups of dissolved metals and sulfuric acid, shelter communities of these hardy microbes that have evolved molecular shields and repair mechanisms to keep their cellular machinery functioning. Even radiation, long considered a deadly force to life, does not spell the end for certain microorganisms. The bacterium Deinococcus radiodurans has earned the nickname Conan the Bacterium for its astonishing ability to survive doses of radiation thousands of times higher than a lethal human dose. It accomplishes this feat by efficiently repairing its DNA and protecting its proteins from damage, showing that life can adapt to survive even the most lethal assaults. In the frozen deserts of Antarctica, life ekes out an existence in cracked ice and beneath glaciers. Microbes survive in briny veins within the ice, metabolizing slowly in temperatures that hover far below freezing. The combination of extreme cold, dryness, and isolation might seem like a recipe for lifelessness, yet here too, life endures. And then there are organisms that inhabit places laden with toxic chemicals, such as deep underground mines saturated with heavy metals and radioactive elements. These microbes have evolved to detoxify their surroundings or simply to withstand poisons, turning Earth's most dangerous places into sanctuaries for life. What do all these extremophiles teach us? They reveal that life is not a fragile miracle needing ideal conditions. Instead, it is an incredibly robust, adaptable process capable of exploiting niches we once considered unlivable. This realization expands the horizons of the search for life beyond Earth. If life on Earth can survive in boiling heat, crushing pressure, acidic soups, radioactive wastelands and freezing ice, why shouldn't life find a way on worlds vastly different from ours? Consider Jupiter's moon, Europa, a frozen orb beneath whose icy crust scientists believe there is a vast ocean. Though the surface is bombarded by intense radiation, the ocean beneath may be warmed by tidal forces, harboring hydrothermal vents like those on Earth's ocean floors. If Earth's vent ecosystems can flourish without sunlight, perhaps Europa's hidden ocean could as well. Saturn's moon Enceladus also displays plumes of water vapor and organic compounds erupting from beneath its icy shell, hinting at an underground ocean that might be habitable. Titan, with its lakes of liquid methane and ethane, represents an entirely different chemistry, a frigid world where life, if it exists, would need to be radically different from our own. Even Mars, long considered barren, has revealed traces of water ice and complex organic molecules, suggesting that in its ancient past, it might have supported microbial life. Extremophiles, therefore, are more than biological curiosities. They are blueprints for possibility, proof that life's definition must be flexible, that the boundaries we once imagined are porous and shifting. They encourage us to dream not only of microbial life on distant worlds but to imagine the forms that might take, shaped by alien environments. As we peer into the cosmos, scanning distant planets for signs of life, these creatures teach us a crucial lesson. Life is resilient, inventive, and stubborn. The universe is vast, and where conditions allow even the slightest foothold, life may grasp it with tenacity beyond our wildest expectations. And so, when we imagine encountering life beyond Earth, we must remember that it might be thriving in places we least expect. In the boiling acid pools of distant moons, in crushing pressures beneath icy shells, or in radiation fields that would annihilate us. These extremophiles challenge our assumptions, stretch our imaginations, and light the path for our cosmic search. They invite us to ask not just if we are alone, but what strange, wonderful, and resilient forms of life might be out there waiting to be discovered. Picture a place where boiling water bubbles and poisonous gases swirl, where nothing should survive, yet life thrives there. What does that tell us about the possibilities waiting on worlds far beyond our own? When you imagine the search for life beyond Earth, it's easy to picture distant sparkling stars and far-flung planets orbiting them. But before we dream too big, there's a fundamental question we must answer. Where exactly do we look? What makes a planet or a moon a suitable home for life? How do scientists decide which worlds might harbor living organisms, or at least the raw ingredients for life? The search begins with something called the Goldilocks zone. This poetic term captures the idea of the habitable zone, a region around a star where temperatures are just right for liquid water to exist on a planet's surface. Not too hot, so water evaporates into space, not too cold, so water freezes solid. Earth sits perfectly in our sun's Goldilocks zone, bathed in sunlight just enough to keep its oceans flowing, its plants growing, and its creatures thriving. But life's story is far more complex than just temperature. The Goldilocks zone is a good starting point, but it's not the whole picture. It's more like a welcome mat outside the door, inviting life inside. But what awaits beyond depends on many other factors. One crucial piece of the puzzle is a planet's atmosphere. Our atmosphere acts like a blanket, trapping warmth and protecting life from harmful radiation. It also holds water vapor, regulates climate, and carries oxygen for animals to breathe. Without the right atmosphere, a planet, even one in the Goldilocks zone, would be a barren wasteland. Take Mars, for example. It sits close to the inner edge of the sun's habitable zone. Billions of years ago, Mars had a thick atmosphere and liquid water flowing on its surface. Today, however, its atmosphere is thin and fragile, leaving its surface exposed to the harsh solar wind and freezing temperatures. Yet beneath that cold, dusty surface might lie pockets of water ice, and even liquid water briny enough to sustain microbial life. The story of Mars reminds us that the habitable zone is a dynamic concept, shaped by planetary evolution over millions of years. Another essential shield for habitability is a planet's magnetic field. Earth's magnetic field deflects charged particles from the sun, known as the solar wind, preventing them from stripping away the atmosphere and bombarding life with deadly radiation. Mars, lacking a global magnetic field, suffered atmospheric loss, a fate that makes its surface increasingly hostile. Understanding whether distant worlds possess such magnetic protections helps scientists refine their search. The presence of water, of course, remains the ultimate litmus test. Without water, the chemistry of life as we know it cannot function. But water need not be visible on the surface to be significant. Scientists now know that some of the most promising habitats might lie hidden beneath thick layers of ice. Jupiter's moon Europa is one such place. Its icy crust, cracked and creviced by tidal forces, conceals a vast subsurface ocean, possibly twice the volume of all Earth's oceans combined. Beneath the ice, heat generated by gravitational tugging creates an environment where life could emerge. Hydrothermal vents on Europa's ocean floor might spew mineral-rich water, just like the vents deep in Earth's oceans, providing the energy and nutrients needed to sustain ecosystems. Similarly, Saturn's moon Enceladus has captivated scientists with its geysers of water vapor and organic molecules shooting out from fractures near its south pole. These plumes indicate an underground ocean kept liquid by the moon's internal heat, again raising the tantalizing possibility that life might be lurking there in the dark, beneath the icy shell. Even Titan, Saturn's largest moon, though colder and chemically different, holds promise. It has lakes of liquid methane and ethane and a dense atmosphere rich in organic molecules. While its chemistry is alien to Earth's, scientists ponder whether life, if it exists there, might have evolved to use methane as a solvent instead of water. This forces us to broaden our understanding of what habitable truly means. Beyond our solar system, astronomers have discovered thousands of exoplanets orbiting distant stars. Some of these exoplanets reside within their star's habitable zone, and others show signs of atmospheres and water vapor. The challenge, however, lies in the vast distances and faint signals, making direct observation incredibly difficult. Yet advances in telescopes and space probes inch us closer to glimpsing signs of life on these alien worlds. Our quest to find life pushes the boundaries of what we understand about biology, chemistry, and planetary science. Each new discovery teaches us that life is a tenacious force, willing to thrive under conditions far more extreme than we ever imagined. When we consider where to look for alien life, we begin to see the cosmos as a landscape dotted with potential oases, hidden oceans beneath ice, warm spots near volcanic activity, atmospheres thick with protective gases, magnetic shields guarding against stellar fury. This chapter in the story of life beyond Earth is one of exploration and possibility. It reminds us that the habitable zone is not a simple ring around a star but a complex interplay of many factors. Temperature sets the stage, but atmosphere, magnetism, water, chemistry, and geological activity write the script. As we send robotic explorers to Mars, design missions to Europa and Enceladus, and develop telescopes capable of peering into distant solar systems, we bring the dream of finding life closer to reality. Each probe, each analysis, each flicker of data adds a new line to our cosmic story. Ultimately, where we choose to look reflects not only scientific wisdom but a profound human hope that in the vast darkness of space we are not alone. Imagine diving beneath an icy crust on a distant moon, plunging into hidden oceans untouched for millions of years. Could tiny life forms be swimming there right now, in darkness we've never seen? When you step outside on a clear night and look up, you're witnessing just a tiny fraction of the universe. Beyond our solar system lies an ocean of stars, each potentially hosting its own family of planets. For centuries, these distant worlds were little more than speculative whispers in the minds of astronomers and dreamers. But in recent decades, a quiet revolution has transformed those whispers into a roaring tide of discovery. The story truly changed with the launch of the Kepler Space Telescope in 2009. For the first time, we had an instrument designed explicitly to find Earth-sized planets orbiting other stars. Its mission was to watch tens of thousands of stars simultaneously, searching for the tiniest dips in brightness caused when a planet crosses in front, what astronomers call a transit. These subtle shadows revealed an astonishing diversity of worlds, from gas giants many times the size of Jupiter to rocky, potentially habitable planets orbiting smaller, cooler stars. The Kepler mission didn't just find planets, it rewrote our understanding of how common planets are in the galaxy. The data showed that planets are the rule, not the exception. Nearly every star has at least one planet, and many have multiple. More importantly, among these countless planets, there are many that orbit within the habitable zone of their stars, the sweet spot where conditions might allow liquid water to exist. But finding a planet in the habitable zone is just the beginning. The bigger question is whether these distant worlds could actually support life. To answer that, scientists focus on their atmospheres, the invisible envelopes of gases surrounding the planet. Atmospheres tell us a story about surface conditions, chemical processes, and the potential for life-sustaining environments. Thanks to advances in technology, especially instruments aboard the Hubble Space Telescope and the upcoming James Webb Space Telescope, scientists can analyze starlight filtered through an exoplanet's atmosphere during transits. Certain gases, called biosignatures, act like fingerprints of life. Oxygen, methane, water vapor, and ozone can all indicate biological processes. When these gases exist in particular combinations or quantities, they suggest the presence of living organisms transforming the planet's environment. Take, for example, a planet like Kepler 452b, often called Earth's cousin. Orbiting a star similar to our Sun, it lies comfortably in the habitable zone and has a size just 60% larger than Earth. It's one of the first worlds to spark real hope that Earth-like conditions exist elsewhere. But the challenge remains to peer deeper, to detect its atmospheric composition and surface conditions. Another intriguing find is the planet's orbiting TRAPPIST-1, a tiny cool star less than 40 light-years away. This system boasts 7 Earth-sized planets, 3 of which sit squarely in the habitable zone. Because TRAPPIST-1 is so close and its planet so tightly packed, it offers a unique laboratory for studying how life might arise on different worlds in the same stellar neighborhood. The process of hunting for these worlds is both painstaking and exhilarating. Each new exoplanet discovery triggers waves of excitement and scrutiny. Astronomers debate the implications, analyzing orbits, star types, and planetary atmospheres. They develop climate models to predict weather patterns and surface temperatures, imagining what conditions might be like from scorching deserts to frozen tundras, or perhaps even lush alien jungles. Of course, distance is a formidable barrier. These planets are light-years away, some tens, some hundreds or thousands. Sending probes to explore them physically is beyond our current technology. For now, we rely on telescopes, spectroscopy, and computer models to tease out their secrets. Despite this, the implications of finding an Earth-like planet with signs of life would be staggering. It would answer a question that has echoed through human history. Are we alone? Moreover, discovering life beyond Earth could revolutionize our understanding of biology, evolution, and our place in the cosmos. Would these alien organisms share DNA-based biochemistry like us, or might they use entirely different molecules? Would life be microbial or complex, intelligent or simple? Every answer would open new mysteries. The search beyond our solar system also stirs philosophical and societal questions. How would humanity react to confirmation of extraterrestrial life? Would it unite us, or divide us? Would religions evolve? Would governments collaborate or compete over knowledge and contact? In this new era of exoplanet exploration, humanity's gaze has shifted from the nearby planets of our solar system to the infinite galaxy beyond. Each new discovery draws us closer to the possibility that life may be a universal phenomenon rather than a rare accident. As telescopes become more powerful and missions more ambitious, we move from hopeful speculation toward concrete evidence. The stars are no longer just distant points of light, they are doorways to new worlds and perhaps new neighbors. The story of finding Earth-like worlds is one of curiosity, innovation, and unrelenting wonder. It embodies the very spirit of exploration that has driven humans from the dawn of time. And as we peer further into the depths of space, the dream that we might one day discover other life, other stories, other forms of existence remains as compelling as ever. The search for Earth-like planets beyond our solar system is one of the most profound quests of modern science. A cosmic detective story stretching across decades, shaped by incredible advances in technology and the enduring curiosity of humanity. The evolution of exoplanet discovery. Before Kepler, the existence of planets orbiting other stars was mostly theoretical. For centuries we had only the 8 planets, or 9 once including Pluto, in our own cosmic neighborhood. The idea of planets beyond our sun was tantalizing but unproven. Then, in 1992, astronomers made the first confirmed discovery of planets outside our solar system, orbiting a pulsar, a dense, rapidly spinning neutron star left behind by a supernova. This discovery shattered previous expectations and opened a new field, exoplanet science. But pulsar planets are exotic and unlikely to harbor life. The Holy Grail was finding planets orbiting sun-like stars in regions where conditions might be just right for life. That breakthrough came in 1995 with the discovery of 51 Pegasi b, a hot Jupiter gas giant orbiting extremely close to its star. This was just the beginning. Over the next 2 decades, new methods and instruments refined our ability to detect exoplanets. The 2 primary detection techniques became radial velocity method, detecting tiny wobbles in a star's motion caused by the gravitational tug of orbiting planets. Transit photometry, measuring dips in a star's brightness when a planet passes in front of it, blocking some light. Kepler, launched in 2009, used transit photometry to monitor over 150,000 stars for 4 years. It found thousands of candidate planets, confirming over 2,600 by the end of its mission. These discoveries revealed an astonishing diversity: rocky planets, gas giants, super-Earths, mini-Neptunes, and more. Defining habitability, the Goldilocks zone and beyond. The concept of the Goldilocks zone is central to the search for life. It's the region around a star where temperatures allow liquid water to exist on a planet's surface, not too hot to evaporate it, not too cold to freeze it. But as scientists studied exoplanets, they realized habitability isn't just about distance. A planet's atmosphere, composition, geology, magnetic field, and even its star's activity all influence its potential for life. For example, Venus sits near the inner edge of our solar system's habitable zone, but a runaway greenhouse effect created a hellish environment. Mars lies near the outer edge and lost much of its atmosphere, becoming a cold desert. This complexity means searching for life requires understanding the whole planetary system, from star to surface. One of the greatest challenges is analyzing the atmospheres of distant exoplanets. When a planet transits its star, a tiny fraction of the star's light filters through the planet's atmosphere before reaching our telescopes. Different molecules absorb specific wavelengths of light, creating spectral fingerprints that reveal their presence. Oxygen, methane, carbon dioxide, ozone, and water vapor are key biosignatures, gases that, in certain combinations, strongly suggest biological activity. The James Webb Space Telescope, launched in late 2021, is equipped with instruments sensitive enough to study the atmospheres of smaller rocky planets around nearby stars. JWST can detect subtle signs of habitability and possibly even life. Meanwhile, missions like the European Space Agency's Ariel aim to survey hundreds of exoplanet atmospheres, building a broader understanding of planetary diversity. Among the most exciting discoveries is the TRAPPIST-1 system, located about 40 light-years away. This tiny, cool star hosts 7 Earth-sized planets packed closely together, 3 of which orbit within the habitable zone. TRAPPIST-1's planets are prime targets because their proximity to Earth allows detailed atmospheric studies. Observations suggest these worlds might have atmospheres, liquid water, or even the right ingredients for life. Scientists model their climates, speculate about surface conditions, and imagine the ecosystems that might exist under alien skies. Could these planets harbor microbial life, complex organisms, intelligent beings? The questions fuel imagination and research alike. Our ability to discover and analyze exoplanets depends on advances in technology, not only hardware but software. Powerful telescopes with sensitive detectors capture faint light signals billions of miles away. At the same time, artificial intelligence and machine learning algorithms process vast amounts of data, identifying promising candidates and patterns invisible to human eyes. This combination accelerates discovery. AI helps sift through Kepler's immense datasets and will be key for future missions. Ground-based telescopes like the upcoming Extremely Large Telescope in Chile will complement space telescopes by enabling high-resolution spectroscopy and direct imaging of exoplanets. Most exoplanets are found indirectly, but direct imaging, capturing actual pictures of planets, is an emerging frontier. Planets are faint compared to their stars, making direct imaging difficult. However, new technologies, including coronagraphs and starshades, block starlight to reveal orbiting planets. Already, astronomers have imaged a handful of giant exoplanets and circumstellar disks, offering glimpses into planetary systems in formation. Future telescopes aim to image smaller, rocky planets directly, enabling even more detailed studies of their atmospheres and surfaces. The Drake equation and the search for life. The quest to find life is also informed by the Drake equation, a speculative formula estimating the number of active, communicative extraterrestrial civilizations in our galaxy. Each factor, from the rate of star formation to the fraction of planets with life and intelligent beings, remains uncertain. But discoveries of Earth-like exoplanets increase confidence that life could exist elsewhere. Our growing census of exoplanets refines these estimates, narrowing the search and guiding observational strategies. Finding another Earth-like planet with signs of life would shake the foundations of science, philosophy, and culture. The question, "Are we alone?" touches deeply on human identity. Discovering life elsewhere could redefine our place in the cosmos, prompt new ethical questions, and inspire cooperation or conflict. Scientists and policymakers already discuss protocols for contact, data sharing, and how to handle potential discoveries responsibly. Looking ahead, the next decades of exploration promise dramatic advances. As we stand at the threshold of a new age in space exploration, new telescopes, missions, and technologies will sharpen our view of distant worlds. This will bring us closer than ever to answering the age-old question. With every exoplanet discovered, every atmosphere analyzed, and every model refined, we weave a richer tapestry of the universe's story. One where Earth may no longer be unique but part of a vast, interconnected cosmic ecosystem. The stars that once seemed unreachable are now within our grasp. The dream of meeting life beyond Earth moves from fiction toward reality. Scientists have found thousands of planets, some eerily like Earth. But what would it mean to discover a true twin, somewhere out there, light years away, with the perfect recipe for life? How would that change the story of humanity? Chapter 5. The Drake Equation. How many civilizations are out there? Imagine standing on a dark hilltop under a blanket of stars. Each pinprick of light represents a sun, a potential home to planets, maybe life, maybe civilizations that look up at their own skies, wondering the same thing we do. The Drake Equation tries to estimate just how many of these stars might be hosting intelligent beings capable of communicating across the vast interstellar void. The story begins in 1961 when Dr. Frank Drake, an astrophysicist and radio astronomer, was preparing for the first-ever search for extraterrestrial intelligence experiment called Project Ozma. He wanted a way to estimate how many civilizations in our galaxy might be sending signals into space, signals that we could, in principle, detect. Drake's approach was to break the problem into smaller, more manageable pieces, factors that contribute to the number of detectable civilizations. This equation became a guide, a framework that both encouraged scientific thinking and underscored how much we still don't know. Breaking down the equation, but not in the usual way. Although the Drake equation is often presented as a formula, it's more like a story, a journey from star formation to the rise of intelligent beings. The journey begins with the birth of stars. Stars are the cosmic ovens where planets form, the very foundations of any possible habitat. But not all stars are created equal. Some are massive and short-lived, others small and faint, and only a fraction have planets orbiting them in the right conditions. The equation asks, how many stars form per year in the Milky Way? From there it questions, how many of those stars have planetary systems? This question used to be a guess, but thanks to missions like Kepler and TESS, we now know planets are common, if not ubiquitous. Indeed, nearly every star hosts at least one planet. Next, the equation narrows to the planets that fall within the habitable zone, regions around stars where conditions might allow liquid water, a key ingredient for life as we know it. But even this is an imperfect filter, because life might emerge in places we haven't yet imagined, and many planets in the habitable zone may not be hospitable at all. The Drake equation then asks, on how many of these planets does life actually develop? This is the heart of the mystery. Here, science treads into the realm of hypotheses and debate. On Earth, life began relatively quickly after the planet cooled, suggesting it might be common elsewhere, but without data from other worlds we can only guess. It continues to the development of intelligent life capable of communication, civilizations that develop technology, and those that survive long enough to send signals across the stars. The enormous unknowns. Despite being a scientific tool, the Drake equation exposes our ignorance more than our certainty. The parameters, like fraction of planets where life arises or fraction of civilizations that develop technology, are unknown, and each carries profound uncertainty. Some scientists are optimists, suggesting the galaxy teems with life, possibly even civilizations that have been around millions of years longer than humanity. Others are more cautious, invoking the Great Filter, a theoretical barrier that makes the emergence or survival of intelligent life extremely rare. This wide range of opinions means the equation's answers vary wildly. The number of civilizations might be thousands or just one: us. The search for signals. Listening to the cosmos. While the Drake equation frames the question, SETI aims to answer it by listening for signals. For decades, scientists have used powerful radio telescopes to scan the skies, searching for patterns or messages that don't arise naturally. A beacon from another mind, sent across light years. Despite no confirmed signals yet, the search continues with increasing sensitivity and scope. Newer technologies allow scanning wider bands of frequencies and targeting more stars. The hope is that if civilizations are out there and communicating, we might one day catch their cosmic whisper. Philosophical reflections, the cosmic perspective. The Drake equation is more than a scientific estimate. It's a humbling reminder of our place in the universe. It forces us to confront our assumptions about life, intelligence, and survival. It challenges us to imagine others, beings who may be like us or unimaginably different, who may have faced challenges and questions we can barely comprehend. Whether the equation's numbers are large or vanishingly small, the search itself connects us with the cosmos in a shared quest for meaning and understanding. Conclusion: a question without a final answer, yet. For now, the Drake equation remains a profound framework, a symbol of both our progress and our profound uncertainties. As technology advances and our knowledge grows, some of the equation's factors will become clearer, and the fog of uncertainty may lift. Until then, it invites us to wonder, to explore, and to dream. To keep looking up at the stars and asking the question that has captivated us for generations. Are we alone? Look up at the sky and wonder how many civilizations might be shining brightly like us, trying to reach out. Are we an island in a cosmic ocean or one of countless voices calling into the void? Chapter 6, Fermi's Paradox. Where is everybody? Look up at the night sky, and the sheer number of stars stretching beyond the horizon is enough to take your breath away. Each of those distant suns could, in theory, host planets, worlds where life might have sparked and flourished. With the staggering vastness of the cosmos and the seemingly high probability that intelligent life could exist elsewhere, one question looms heavier than any other. If the universe is so full of stars and planets, why haven't we heard from anyone else? Where is everybody? This haunting contradiction is known as Fermi's paradox, named after the legendary physicist Enrico Fermi, who famously posed this question in the 1950s during a casual lunchtime conversation. Despite its simple phrasing, it encapsulates one of the most profound mysteries of our time. How could the universe be so immense and life so possibly common yet remain silent? The paradox arises from a blend of cosmic optimism and harsh reality. On the one hand, we have the Drake equation, which suggests there could be many civilizations in our galaxy alone. On the other hand, after decades of searching with radio telescopes and other instruments, we have yet to detect any undeniable signals from extraterrestrial intelligence. The universe is about 13.8 billion years old, plenty of time for life to have evolved elsewhere. Many stars are far older than our sun, which means other civilizations could be millions or even billions of years ahead of us in technology and understanding. The cosmic stage seems set for a vibrant interstellar community, yet the radio silence is deafening. So why? What are the explanations that might solve this paradox? One possibility is that life, especially intelligent life, might be incredibly rare. While microbial life could be common, the leap to complex, self-aware and technologically advanced civilizations might be so difficult that it happens only once or a few times in the entire galaxy. This rarity might be due to a variety of factors: the delicate balance of conditions needed for life, the instability of environments, catastrophic events like asteroid impacts or supernovae, or even the chance nature of evolutionary breakthroughs. Perhaps Earth is a cosmic fluke, a rare gem in a vast desert of barren worlds. The Great Filter Hypothesis, a cosmic gauntlet. Connected to this rarity is the idea of the Great Filter, a concept that suggests there are immense obstacles or bottlenecks along the path from simple life to advanced civilizations capable of interstellar communication. This filter might lie behind us, meaning humanity has already passed the most difficult challenges, or ahead, implying a dark fate awaits us. The Great Filter adds a chilling layer of uncertainty. Either we are extraordinarily lucky survivors of a rare cosmic gauntlet, or we have yet to face the most formidable challenges. Civilizations destroying themselves. One grim explanation is that advanced civilizations inevitably self-destruct before they can broadcast their presence across the stars. This self-destruction could come from nuclear war, environmental collapse, or the misuse of powerful technologies. History on Earth gives some cause for caution. Our own species has come perilously close to global catastrophe multiple times, and our future remains uncertain. Perhaps in a cosmic mirror, other civilizations have faced the same crossroads and failed. This raises a sobering question. Is our silence the echo of countless lost voices, civilizations that blinked out just as they reached the stars? The dark forest theory, the universe as a dangerous place. Another fascinating explanation draws on ideas from science fiction, particularly the dark forest theory, which portrays the cosmos as a vast and dangerous place where silence is survival. In this view, civilizations may deliberately choose to stay quiet, avoiding detection to protect themselves from hostile others. The universe might be like a dark forest where every civilization is a hunter trying to stay hidden, fearing that revealing one's presence could invite destruction. The logic here is grim but compelling. Broadcasting your location could be akin to lighting a beacon in the wilderness, attracting predators rather than friends. So, silence is not emptiness but cautious strategy. Even if civilizations exist and want to reach out, the sheer vastness of space imposes severe constraints. Stars are separated by light years, enormous distances that make communication slow and difficult. Signals sent across these distances take years, decades, or even centuries to arrive, and the signals weaken and disperse. Detecting or understanding alien transmissions requires technology that matches or exceeds the senders, and timing must align perfectly. Perhaps we are just too early, or our technologies are not yet advanced enough to catch or interpret these cosmic messages. Some scientists suggest the paradox might be a matter of how and where we search. We have primarily scanned radio frequencies and focused on specific signal types, but what if alien communication uses methods we have not yet discovered? Perhaps they use light signals, neutrinos, gravitational waves, or technologies so advanced that their transmissions are indistinguishable from natural phenomena. Maybe our searches are like trying to hear a whisper in a thunderstorm. This possibility encourages expanding our search strategies and thinking beyond traditional radio signals to find new ways to connect with the cosmos. Are aliens already here? Some have speculated the paradox might be resolved by the idea that extraterrestrials have already visited Earth or are observing us covertly. While popular culture loves this idea, scientific evidence remains absent. Still, this speculation fuels curiosity and underscores how much we have yet to understand about our place in the universe and the potential behavior of alien intelligences. the silence as an invitation. In the end, Fermi's paradox is not just a puzzle or a contradiction, it is an invitation. It pushes humanity to look deeper, to improve our technologies, to explore more thoroughly, and to prepare for the profound moment when we might finally answer the question of whether we are alone. It reminds us of the mysteries yet unsolved and the humility required in the face of the cosmos's vastness. The impact of Fermi's paradox on SETI and scientific thought. The silence we face has profoundly shaped the search for extraterrestrial intelligence, or SETI, a scientific effort dedicated to listening for signals from other civilizations. Since the paradox first gained attention, SETI projects have been motivated both by hope and by the sobering realities it presents. Scientists design ever more sensitive instruments and broaden the scope of their searches, from scanning radio waves to looking for laser pulses or even subtle atmospheric changes on distant planets that might hint at industrial activity. The paradox, rather than discouraging scientists, fuels their curiosity and pushes the boundaries of technology. SETI researchers often grapple with the same questions posed by Fermi's paradox. Are we looking at the right frequencies? Could alien signals be encoded in ways we cannot yet decipher? Should we send messages ourselves, or remain silent and wait? Each choice is a gamble, influenced by the paradox's many possible answers. The philosophical and cultural ripples. Fermi's paradox also echoes beyond the scientific community, touching philosophy, culture, and even ethics. It forces us to confront uncomfortable possibilities about humanity's uniqueness and vulnerability. If intelligent life is extraordinarily rare, it places a heavy responsibility on us as stewards of a potentially unique form of consciousness. We may be the universe's first or only technological civilization capable of shaping its destiny. On the other hand, if countless civilizations have come and gone, succumbing to self-destruction or cosmic disasters, it serves as a cautionary tale, a mirror reflecting what could happen if we fail to safeguard our planet and ourselves. The paradox invites deep reflection on what it means to be alive in the vast cosmos and how we might prepare for contact, or the continued silence, in a universe that may be less crowded than we hope. Looking ahead, the paradox drives new questions. Could artificial intelligence help us detect faint signals buried in cosmic noise? Will we develop technologies that allow us to travel or communicate faster than light, overcoming the barriers of distance? Some scientists speculate about revolutionary concepts like quantum communication or harnessing gravitational waves for messaging, ideas that seem like science fiction today but could redefine our ability to connect. Meanwhile, upcoming space missions aim to analyze exoplanet atmospheres with unprecedented detail, searching for signs of life's chemical fingerprints. The combination of technological innovation and interdisciplinary research might finally crack the paradox open, transforming silence into conversation. Embracing the mystery. Despite decades of searching and theorizing, the paradox remains unsolved, a riddle wrapped in starlight. But this mystery is part of the allure of space exploration, the tantalizing possibility that discovery is just beyond our reach. Whether we find signs of life tomorrow, centuries from now, or never at all, Fermi's paradox challenges us to keep looking, keep learning, and keep wondering. It reminds us that in the vast darkness of space, the most profound light may come not from distant stars, but from our own curiosity, resilience, and hope. The universe is vast and old, so why is it so quiet? Could it be that advanced beings choose silence? Or maybe, just maybe, we're not ready to hear what's out there. Chapter 7. What would humanity do if we discovered aliens? The moment arrives. After years, maybe decades of searching, telescopes pick up a signal so clear, so unmistakable that the world stops. A message from somewhere beyond the stars, unmistakably artificial, unmistakably alive. It is no longer a question of if but when, and now that when has come. What happens next? How would humanity react to the knowledge that we are not alone? At first, the reactions would be a swirling storm of emotions. Imagine the initial shock, like a collective gasp echoing across every continent and culture. Some would feel a rush of exhilaration, the validation of a cosmic question that has haunted us for centuries. At last, proof that the universe teems with life, that somewhere else out there, intelligence peers back at us. Yet alongside the exhilaration would be fear. Fear of the unknown. What do these beings want? Are they friends or foes? Could their arrival mean the end of our way of life? This fear might spread swiftly through populations, especially given humanity's long history of fearing the other. It would be natural to wonder if this contact might bring conflict or even extinction. Governments would suddenly find themselves at the center of a new kind of challenge. Would they unite, putting aside political rivalries in the face of a universal discovery? Or would competition intensify, as nations scramble for control over knowledge, technology, or even potential alliances? History suggests it could go either way. During global crises, humanity has shown both astonishing solidarity and terrifying fragmentation. Religions, too, would be deeply affected. Some might see the discovery as confirmation of their beliefs, others as a challenge to centuries of doctrine. Would faith evolve, incorporating this new cosmic reality? Or would there be resistance, fear, or even denial? The discovery could spark profound theological debates, perhaps reshaping how humanity views its place in the cosmos. On a personal level, individuals would wrestle with their own beliefs and hopes. Philosophers and scientists would ponder the meaning of life itself. What does it mean if we are no longer unique? Could we learn from alien wisdom or technology? Would it inspire a new era of curiosity and exploration? Yet there's also a risk. Contact might inflame existing divisions. Some might reject the news as hoaxes or conspiracies, others could exploit the moment for power or profit. Fear might be weaponized, driving discrimination or paranoia. Despite these risks, the discovery of extraterrestrial life holds an incredible potential to unite humanity with a shared purpose, a cosmic perspective beyond borders and divisions. The knowledge that we are part of a larger community of life could foster empathy, cooperation, and renewed respect for our fragile planet. History offers clues in how humans have reacted to encounters with the unknown. When explorers first crossed oceans, it brought wonder and tragedy, curiosity and conflict. The discovery of alien life would be even more profound, challenging everything we thought we knew. In the end, what humanity does depends on us. The choices we make individually and collectively. Will we rise to the occasion with wisdom and courage, or will fear and division prevail? The story of our response to alien contact is still unwritten, but one thing is certain: it will be one of the most defining moments in human history. Imagine the day a message arrives or we find undeniable proof of aliens. Would it bring us together as one or tear us apart? How would faith, politics, and everyday life change overnight? Humanity has long dreamed about the moment of first contact, the instant we discover, or are discovered by, another form of intelligent life beyond Earth. But this dream, which has fueled countless stories, movies, and philosophical debates, is no longer just fantasy. Scientists, policymakers, and ethicists around the world are actively preparing for that moment, debating how we should respond and what the consequences might be. The question is no longer if, but how. This chapter dives into the complex scientific and ethical challenges we face in preparing for contact with extraterrestrial life. It is a journey into humanity's readiness, or lack thereof, to greet the unknown, filled with hope, caution, and profound uncertainty. Since the mid-20th century, when the search for extraterrestrial intelligence, or SETI, began to take shape, scientists have understood that the discovery of alien life would not be just a scientific milestone, but a profound cultural event. As such, formal discussions about first contact protocols began. One of the earliest formal efforts came in 1989 with the publication of the Declaration of Principles Concerning Activities, following the detection of extraterrestrial intelligence. This document, endorsed by various space agencies and scientific bodies, laid out tentative steps for how humanity should respond if an alien signal were detected. It emphasized transparency, urging that the discovery be shared openly with the global public, and discouraged any rash or secretive reactions. But while this declaration offers a foundation, many questions remain unanswered. How do we even formulate a reply when we don't know what language, if any, an alien species uses? What kind of message would be appropriate or safe to send? And beyond communication, how do we prepare for the possibility of physical contact, or worse, a hostile encounter? Sending and receiving messages across the cosmic void is more complicated than it sounds. Human languages are full of nuance and cultural context, often relying on shared experience and symbolism. How can we possibly design a message that an alien mind could understand, or that they could respond to in a meaningful way? Scientists have tried to think outside the box. One famous example is the Arecibo message, a 1974 radio broadcast aimed at a distant star cluster, which encoded basic information about humanity, our DNA, and our solar system in binary code. The idea was to use mathematical and scientific constants as a universal language. Numbers, prime numbers, the structure of atoms, these are thought to be the building blocks of an intelligent message that might transcend biology and culture. But even this raises problems. We assume aliens would recognize these concepts or symbols, but what if their cognition is completely alien? What if their senses don't rely on light or sound, or their perception of time differs from ours? Could we miss an important nuance or unintentionally send a message that could be misinterpreted? Beyond just sending messages, scientists debate whether we should respond at all. Some argue for a listen-only approach, fearing that broadcasting our presence might invite risks. Others believe that an active dialogue could usher in a new era of cosmic cooperation. This debate is far from settled. The ethical challenges of contact are staggering. If we receive a message or find physical evidence of alien life, who decides how to respond? Earth is home to nearly 8 billion people with diverse cultures, beliefs, and political systems. Should a handful of scientists or politicians make decisions that affect the entire species? International organizations like the United Nations have started to discuss these issues, but there is no clear framework. What if countries disagree on the appropriate response? What if certain groups try to exploit the discovery for power or profit? Furthermore, there are deeper ethical questions about the nature of the life we might encounter. What if the alien life is microbial or animal-like? Do we have a responsibility to protect it? If we discover an intelligent civilization, what rights do they have? How do we avoid repeating the mistakes of colonial history, where one culture imposed itself on another, often violently? Science fiction often dramatizes the threat of hostile aliens invading Earth. While such scenarios are speculative, scientists take the possibility seriously, especially given humanity's limited knowledge. One concern is biological contamination. Just as astronauts take extreme care not to contaminate other planets with Earth microbes, the reverse is also a risk. Alien microbes, if brought back or encountered, might be harmful. The 1970s protocols during the Apollo missions were cautious, requiring quarantine for astronauts returning from the Moon, even though the Moon was thought sterile. Future missions to places like Mars or Europa could bring back unknown organisms, raising biohazard concerns. Moreover, if extraterrestrials possess technology vastly superior to ours, the balance of power could be dangerous. Even if they mean no harm, their arrival could disrupt ecosystems, economies, and societies. Their technology might be so advanced that it is incomprehensible or impossible for us to control. The importance of international cooperation and transparency. Given these risks and ethical challenges, many scientists emphasize that no single nation or group should control humanity's response to first contact. This is a global event, one that requires openness, dialogue, and cooperation. International bodies like the United Nations could play a crucial role in coordinating responses, establishing protocols, and ensuring transparency. Information must be shared openly with the public to prevent misinformation and panic. The rise of social media means rumors and conspiracies could spread quickly, so clear communication will be vital. Some countries have already established working groups focused on extraterrestrial contact, and collaborations like the International Academy of Astronautics have put forth guidelines, yet much work remains. The role of humility, recognizing our place in the universe. Perhaps the greatest challenge in preparing for contact is psychological. Humanity's ego and sense of uniqueness have been challenged before, when we learned Earth is not the center of the universe, or when we realized other species share complex emotions and intelligence. The arrival of alien life will force us to confront our own place in the cosmos more deeply than ever. This requires humility, an acceptance that we may not be the most advanced or significant species. It challenges long-held beliefs and worldviews. Humility also means approaching contact with an open mind, ready to learn and adapt. It means resisting fear and arrogance and instead fostering curiosity, respect, and patience. Preparing our minds and societies. Scientists and educators have begun to consider how to prepare the general public for the possibility of contact. Education about astrobiology, SETI, and the history of life in the universe can help demystify alien life and reduce fear. Psychologists warn that people might react with denial, panic, or existential anxiety. Social institutions will need to provide support and leadership to navigate these emotional challenges. On the flip side, contact could inspire new scientific endeavors, artistic movements, and cultural exchanges that enrich humanity. It could be a moment of unity, a collective step toward a shared destiny. Preparing for the unknown, embracing uncertainty. No matter how much we prepare, first contact will be unpredictable. The universe is vast, and alien life may be unlike anything we can imagine. The only certainty is uncertainty itself. Scientists advocate for flexible protocols that can adapt to new information and situations. They emphasize ongoing research, vigilance, and dialogue. The act of preparing for contact is itself a reflection of humanity's curiosity and hope, a testament to our desire to understand the cosmos and ourselves. In the end, preparing for contact is not just about science or technology, it's about ethics, philosophy, diplomacy, and culture. It's about who we are as a species and how we face the great unknown. If the universe is listening, what should we say? And how do we prepare for a meeting that might challenge everything we believe about ourselves? Are we truly ready for that moment? Conclusion. The journey ahead. The quest to discover whether we are alone in the vast cosmic ocean is more than just a scientific endeavor. It is at its core a profound journey of self-discovery. As we peer into the night sky, seeking faint whispers of distant worlds, we are also reflecting inward, questioning who we are, what it means to be alive, and how we fit into the grand tapestry of the universe. Each signal scanned, each new exoplanet cataloged, and each extremophile unearthed on Earth is a step closer not only to finding alien life, but to understanding the resilience, diversity, and potential of life itself. Whether the answer lies just beyond the next star or remains forever out of reach, the pursuit reshapes our perspective, deepening our appreciation for our fragile planet and our shared humanity. If we find life tomorrow, it will be a revelation that forever alters the course of history, challenging our philosophies, religions, and sciences. If it takes centuries or even millennia to find a trace of the cosmic neighbors we imagine, the search will still unite us in wonder and perseverance. In this endless quest, hope fuels our curiosity, Courage steers us through uncertainty, and respect for the unknown keeps our minds open. We are explorers of the stars and keepers of dreams, forever reaching beyond the horizon, propelled by the timeless question, are we alone? The journey ahead is uncertain, vast, and awe-inspiring, but as long as we keep looking up, humanity's story will continue to unfold among the stars. As you watch the stars tonight, think about this. What part will you play when humanity finally answers the question that's haunted us forever? How will this journey change your view of our place among the stars? Thanks for joining me on this incredible journey into the unknown, the search for alien life and what it might mean for all of us. If there's one thing this exploration shows, it's that curiosity is at the heart of being human. No matter what we discover out there, it's the questions we ask and the courage to keep looking that truly define us. If you enjoyed this deep dive, don't forget to like, subscribe, and hit that notification bell so you never miss a video exploring the mysteries of our universe. I'd love to hear your thoughts. What do you think would happen if we ever found aliens? Drop your ideas and questions in the comments below. Until next time, keep looking up, keep wondering, and remember, the universe is bigger and more amazing than we can imagine.